All right, good morning.
Hello.
Good morning, both of you, because we've got two people in class. Um,
You left a comment on my PA4 and said that my restart button didn't work, but I tried it last night and it seemed to be working for me.
okay, I'll go back and recheck it. It was a lot of dots
Is it
games.
possible that it was supposed to always be active? Because the restart button only worked after the game was over.
Oh no, it should be able to restart while the game's playing.
Oh, that wasn't in the PDF.
Oh, okay.
It did say that it should be active during playing though. So
Yeah, the way it was phrased, it came after, like, when you described the end of game, after the game was over.
it didn't describe end of game. The PDF didn't describe end of game at all. It didn't even say that the game actually had to say that it ended and whatnot, if I recall correctly.
Yeah, I didn't talk a lot about the restart.
I assumed that Nick wasn't gonna play through an entire game of 9x9.
Yeah.
Well, I had an option in mind. You could just quickly put in a one by one if you wanted to test it.
Yeah.
Well, he wouldn't be able to get to that without restarting, no? Oh, what do you...
So there should also be a restart button which will completely reset gameplay to the beginning.
Yeah, and that comes after the thing that says if the game has been completed.
Right.
Yeah,
There should also be.
completed, the game should note this and report who won, and then after that you talked about a restart button. So I figured the restart button came after when the game was over.
Okay, I thought I made that clear when we first talked about it, and I talked through the demo, and I showed the restart button. But okay. All right. So other questions? Was that a question or a thought? Because it.
Thinking.
Okay. Could have easily been a Zoom misfire.
For sure. Okay, here's my question.
Okay.
In my PA4, I wanted to separate out functions to each of the classes
Mm-hmm.
a lot, and so I ended up doing a lot of calling up and I know down calling is fine, but I ended up doing a lot of calling up. Is that something that would be frowned upon and like something that would be considered not clean, or is
So
it totally fine?
what do you mean by down calling or calling up?
Well, by down calling, right? I guess I mean you create a class, right? Or you go file name random variable equals new file name, and then you call a function in that class.
Mm-hmm.
So that'd be like down calling, I guess. I don't know.
Okay.
And then up calling is you inside of that class it makes a call up to the parent.
I think either of those is fine.
I was just wondering if calling functions in a class is always totally fine, but calling functions from the class to the parent, I do it a decent amount, and I guess I don't know whether or not that's clean or not.
So in my view, which is just my view, right? It's most important to put the methods where they belong, in the class that they belong to. So if you have a piece of data inside a class, the method that interacts with that data should probably be in that class in general, right? Broad brushstrokes here. It's entirely reasonable that something in a different class might want to interact with, a property from some different class, but I would say, yeah, leave the method in that different class, the same class that has the property, and call it from that other class. So think of setters and getters, right? I might want to access a field in a class that constructed me. I don't think that makes things more confusing or anything like that. I think the alternative, which would be to somehow, copy those methods, or make a second method that does the same thing in this other class, just because this class was called by this other class. I think that would potentially make things a lot more confusing. So it sounds like what you did was probably the right way to do it.
Okay. Yeah, I guess the alternative would just be to do more work in the parent class. Or,
Mm-hmm.
They just, I don't know.
Yeah, I mean,
Ventriloquism skills are really on point right now.
say again?
Your ventriloquism skills are on point right now.
They are. How about that? Yeah, so I think we should be very comfortable, invoking methods from objects wherever we need to do something to interact with that object, and probably not worry about, well, but I was created by this other thing, and so I have to use my parents' methods or something. I think that's totally fine. Yeah, I'm just gonna kill this camera because this has been a bad morning for computing. I was trying to run Verilog software in 250, and it was giving me all kinds of headaches. And I think my CPU is a little overloaded. This will be one nice thing about being back in person is I'm going to simplify my presentation.
So you'll be in higher frame rate.
I'll be in higher frame rate, and I'll probably be in a mask, but I've already got, a microphone to project my voice, and I'm leaning towards... Yeah, well, you could retake 270, right?
Well, I haven't taken 270.
Oh, okay.
In the summer, I think.
Okay.
Speaking of, I need to apply for that.
Yeah.
I think that's too late.
I think there's still sections. I've only got like 10 people in my section, so I know my section has openings. I think Izad's does also. I believe Izad is...
270 in summer, but logistically, if you're trying to go to like WSU or whatever, you have to do like sort of dual enrollment, and it gets a little hairy.
The last couple of weeks, you can find yourself taking like 40 credit hours, but it's usually not a big deal. I know when I teach 270 in summer, if somebody has, class conflicts with WSU, we usually work around it. And then for the final exam, maybe you have to miss a class at WSU or something. But, I think both sides usually understand that this happens. And,
What time does summer class courses end?
For Clark?
Yeah.
You're
saying that it overlaps with the beginning of WSU.
Yeah, it usually overlaps about 1 or 2 weeks.
I think the summer classes end like August 30th or something.
Something like that, yeah.
Oh boy.
WSU starts August 20 something.
Okay. Yeah.
Usually, I think last year they started on the 23rd.
Okay. So yeah, there's a little overlap sometimes, but like I say, it's usually something that you can work with the instructors on to make it feasible.
I plan to take my WSU physics class in the summertime, starting on June 6th, I think. So that's when my summer class starts for
Okay.
WSU. And I think it ends around like the end of August.
Okay. So you'll be overlapping with spring quarter by a week, I think.
Yeah, a little bit, but that's only like the first few weeks.
Yeah.
The last few weeks of spring quarter.
Okay.
Question.
Yeah.
Is your engineering 270 in person or online?
It's gonna be in person.
Ugh, hang it.
Yeah. I'm not thrilled with it, but that's the pressure from the school, so.
Alright, odds at 8 it is.
Yeah. Early but remote, so.
Well, I'll be working full time, which I guess won't be full time anymore. I hoped it'd be straight online, but apparently not.
Yeah. And Izad's classes are great. I would take 270 from Izad if I was a student. All right. Other questions, comments? So PA4, I've graded and posted feedback where applicable. Got a few that I think are still coming in today. Surprisingly to me, almost nobody worked in a group, which I find interesting. So group work is an interesting proposition. It's theoretically advantageous to work with other people, but it brings its own challenges, right? Coordinating and trying to balance load, and if you're dependent on other people doing their part for your grade, that can be kind of a scary or risky proposition. And I don't know what went into people's decisions, but for whatever reason, I think I had at most two people working in two groups for PA4, and everybody else was working alone, which is fine with me. When I was in school, I always preferred to work alone until I eventually found someone who I worked really well with, and then we always did projects together. But it's a kind of a tricky business working in a group. Now, my suggestion on PA4 was, even if you're in a group, everybody do the project yourself, right? But take advantage of the group aspect to say, hey, let's talk about such and such. And I think that's still, a worthwhile consideration, being able to, kind of legally share your code and talk about code and get ideas from the other people in your group. But for whatever reason, most people worked alone. Nonetheless, most people got PA4 working, either working pretty much perfectly, maybe a few minor things here and there, or got to a point where they decided, okay, I don't have enough time to finish this, and so I'm going to get these pieces working, and then they generally got these pieces working and got the grade that they expected from that. So that looked pretty good, and this is really critical because PA4 is the building block for PA5, right? PA5 is the networked version. So what I've been telling people is, if they're still struggling with PA4, get it turned in, right? Get whatever points you can, but then really quickly try to finish up PA4 so that you can build on it for PA5. Don't try to do them at the same time. Get the single machine version of dots working, and then start adding the networked layer to make it multiplayer. But definitely get the single machine version first. All right, and I'm not gonna share sample code for PA4 because assignments are still coming in, and it's a part of PA5, so we can go through sample code maybe at the end of the course, but I'm gonna hold off on that for now. All right. Well, let's take care of this business of radio buttons. It's one aspect of PA5 that we haven't actually gone through an example of in Eclipse. So let me just talk about radio buttons for a few minutes. So if you ever had a nice old car with like a mechanical radio button setup, you know what radio buttons are. It's usually a set of buttons, and you press one button and the other button that you had pressed before pops out. And this was how preset stations on car radios were configured back, in the analog days. And you could preset a particular station by dialing in a station and then pulling the button out. And if you pulled hard enough, it would actually come out, so it would be less pressed than all the other buttons. And then you push it in all the way, and it mechanically would lock in that dial position to that button. So now you have these buttons you can just press and the dial jumps to some predefined location. But the key to that mechanism was, you know, if you had one button pressed and then you pressed a different button, the first button would pop out. So only one button was pressed in at a time, and you could tell what station was preset. So we can emulate this in Swing. And there's only one small detail to set up. So let me start with a J-frame. And let's go into our design window. And as usual, I'll put my absolute layout in here. And so let's drop a radio button in here. And we'll drop another one right next to it, and we'll drop a third one. And let me just throw some text on here. So this is the do something. This is the do something else. And this is the do nothing button. Alright, so if I run this, I get a window that pops up. It's got my 3 radio buttons. But they don't act like radio buttons. I can like select or deselect each of these, and they're independent of each other. So they're not doing that radio button thing for which they're named, right? So if I right click on this, I can say set button group, and I don't have any button groups right now. I can say let's create a new standard button group. All right. And so now, if I look at this thing, button group, it's in this thing called button group. So if I right click on this second button and I say set button group, I can set it to that same button group. And now if I run my program, these first 2 buttons are locked together into a single group. And I can only press one button from those. This third button is in its own group, so it's unaffected by these, and this does not affect those 2. So if I wanted a 3-button radio button setup, I could take this and I could set the button group to also be button group. And now I've got, you know, my 3 buttons that only allow me to set one. So that's the only kind of small trick there is that set button group option. If I pick one of these, I can also say it's selected is true. And now when I run, you know, that's the first button that's always selected, and I can pick a different one instead. So for PA5, you know, client server or server client, you can do it like that. And these buttons, so let me throw a regular push button in here. And let's write some code. So, let me name these buttons differently because these are horrifying names. So call something, let me call this button 1. These are even worse names now. Let me call that button 1, let me call this button 2, let me call this button 3. Don't do this. Don't use names like B1, B2. But I'll waste our whole class if I try to give these good names. Alright, so I have these buttons called B1, B2, B3. So let's just do some print statements here. Alright, so a radio button comes with an isSelected method, which will tell you whether or not that button is selected. And so I'm just going to, when I press that push button, I'm just going to print out the value of the isSelected method for each of my 3 buttons. And so if I do this, it tells me button 1 is selected, the others are false. If I switch to this button and I press my push button, it says button 1 and 3 are false, button 2 is true. So you can find out if a button is pressed by just calling its isSelected method. And so in your PA5 code, when you're ready to start, you can check that method return value to see whether a button's been checked or not. The other thing we can do is we can add an event handler. And this usually takes a few tries. Let's try item state changed. And I'm just going to print a method in here, put a print message in here. And so if I make some change on selecting or deselecting that first button, that method gets called. And so in PA5 we have this requirement that if you are the server, your window looks one way. If you're the client, your window looks a different way. And so we can put code into item state changed for both of those. And in either case, we can just say, update the display based on server client radio button, or whatever we want to call it. And then that would go ahead and, change the start button to say connect or start, and so on and so forth. So that's it for radio buttons. But questions about that? All right, and then I think we already talked about this. But I think it was Wednesday that I got tangled up with this business of trying to run your program twice inside Eclipse. And so I posted a video about this, but just to rehash, right? You can create a new console view by coming down here and saying new console view. You can drag and drop these around to put this in different places and so on and so forth. So whatever your preferred layout is. And then this is the way things are normally set up. So when you hit the new button, you get output on both windows. And so the trick here was to find this button which says show console when standard out changes. Uncheck that, right? And it's pretty subtle. It's either like grayed a little more or it's got the background color. So click it so it's got the background color. And then you can take each of these consoles and you can choose which window you want to display. So up here I'm going to display my first window, and down here I'm going to display my second window. And now when I hit this button, it comes out in that top window, and when I hit this button, it comes out in the bottom one. And so that's how you can get to 2 instances of your code running in Eclipse, but with separate output windows that you can use to interact with it, and also separate stop buttons, so I can stop that first one, and then I can stop the second one. All right, so let's we're done with Eclipse for today. Let's talk more about client-server concepts. So we introduced this last week, this idea of a server and multiple clients. And each of these can connect to the server and have the server act on its behalf. And so to do this, the server needs to have an address. And it's got to be an address that each of the clients knows about. If you want to get a web page from clark.edu, you've got to know, that you're going to clark.edu. And if you're trying to access the web browser at Clark's site, you've got to know the port number of that, which is, probably 8080. And so this address is associated with, a server, and it's hardwired, it's bound to it, right? The client doesn't really matter what my address is, right? As long as I know the address of the server, I can call someone from any phone, and it doesn't really matter what my phone number is. The thing that matters is what's the connection information for the place I'm trying to reach. And so in a typical client-server setup, the clients will have, whatever addresses they have. They're on whatever machine they're on, and their port number, that particular part of the address we talked about Wednesday, will vary from client to client and from run to run. But the server has a particular internet address and a port number. All right, so what's the IP address? Something dot something dot something dot something. It's a 4-part address. Each of these is a number from 0 to 255, so that's 32 bits. This is sometimes called IPv4. And we ran out of, address space years ago, so we're slowly moving to IPv6, where we have more bits available. But for us, we're just going to stick with IPv4. And so, for example, if I say ifconfig, I have a wireless connection on my laptop at 192.168.0.136. And I have a hardwired connection, it's a good old cable, at 192.168.0.101, right? These are local addresses. If you try to telnet to 192.168.0.101, you will not reach my laptop. You'll possibly reach something on whatever local network you're running on, right? But these are local networks. And 127.0.0.1, that's the loopback address. That's always a reference to myself. That's the address I said you can use in your PA5 to, have both people playing the game on the same machine, 2 different instances. But somewhere out there is a 4-part network address corresponding to the part of my network that connects to the outside world. That's the router. And so, that might be 76.14.2.38. And so anyone, anywhere on the network, if they try to address a server at this IP address with port 1234, they would connect to my NetDots server. And they'd be playing a game against me, across the network. So we talked about sockets. We talked about sockets as being, the type of structure that's used to make these connection points. And in Java, there's 2 entirely separate classes for making these sockets. There's something called a server socket, which we use up here, and there's just a plain socket, which we use down here. And so we started to put together some code, and let's pick up where we left off. So the server socket class we constructed by specifying a port number, and the address part of the server socket, right, this part right here, the IP address and so on, we don't get to specify that, right? That would be a big security nightmare if we could say what our IP address was when we constructed a socket. So the server socket's address is always the address of the machine that we're running on. The part we specify is the port number. Which of the 65,000 possible socket locations on our machine do we want to use? So we're going to construct with a port number. And so we're going to do something like this. And so try catch blocks, because this constructor can throw an exception, IO exception, security exception, illegal argument exception, lots of exceptions possible. So I'm just going to do this in a general try block. So I'll construct a server socket on port 1234. And then after constructing, I'm going to call the method accept, and accept will listen for connection requests. So I create a server socket that makes a socket with this given port number that is able to be connected to by clients. But you can't connect until I tell the system, okay, I'm ready to accept connections from here. And so I'm going to say ss.accept. And my comment here is receive a connection. So I'll make a socket for others to connect to, and then when I call accept, that will be receiving the connection, right? And I'm going to save the return value from accept, which we're told is a socket. So listen for a connection to be made and accept it. The method blocks until a connection is made. So this call will not return until somebody connects to me. So I'll close my try catch block here. Alright, so kind of boilerplate stuff here, right? My accept is going to return a socket, and so I need to declare this. So this will be the socket we get after accept returns, and so I'm going to need to import socket. And socket has its own documentation. And we can construct a socket, you know, in a variety of ways, but most commonly by specifying an internet address and a port number. So on the client side, if we wanted to make a client to talk to a server socket, we would say I want to talk to, you know, this address, this port number. And we put those in the constructor. But in this case, we're on the server side, so when we say accept, it's going to give us a socket. And so the way this actually works is, here's your server, and it's sitting at some port. So as an IP address plus a port number. And then here's a client. And the client makes a socket and makes a connection request. And the accept call from here creates a new socket. And this new socket is connected to the client socket. And so now we have two-way communication going like this. And if another client comes along, it can make a request to the server. And if the server accepts that, it will create a new socket and set up two-way communication with the client through that new socket. And so in this case, port 1234 is always going to be waiting to accept a connection. And whatever client comes along will be able to connect to it, and a new socket will be created. And now you have two sockets connected together. But we're going to do this one single connection at a time for simplicity's sake. So we're going to make our server socket accept a connection, and let's just print something here. Let's just print out the socket. Let's get rid of our typos. Alright, so there's our main program running. And I mentioned you can use telnet as an easy way to make connections to sockets on any machine that's listening for connections. So I can say telnet localhost, and let's go to port 1234. And my Java program tells me, hey, I received a connection. Here's what the socket was that was returned by the accept call. It came from address 127.0.0.1, and the port number of this client socket that was created, right, was port 33844, whatever that means. Now if I try to connect again, it's not going to work because there's nothing listening for a connection on port 1234. Alright, so this was around where we left off last week. Let's expand on this. So let's send a message to the client. So we're going to use a PrintWriter for writing into this socket. So we're going to need a PrintWriter. And while I'm in here, I'll set up our scanner import. And I think PrintWriter comes from I/O. Yeah, java.io. Alright, so how does this work? Well, PrintWriter, if you look at the constructors, we've been constructing it with a file, right? But we can also construct it with something called an output stream. Well, if you look at socket and you look at the methods, there's a method called getOutputStream, and it returns an output stream for this socket. So we can put these together. So let's make a PrintWriter for sending to the socket. I'm going to call my PrintWriter toClient. I'm going to start moving away from, PW for the PrintWriter and SC for the scanner. Because as we move further into this client-server world, we're going to find that there's some potential confusion. For example, sometimes the client is going to want to send information to the server, and sometimes the server is going to want to send information to the client. And if I just call PW the print writer that I construct, well, this is going to have a PW, and this is going to have a PW, and I'm going to end up calling them PW1, PW2, or something kind of uninformative like that. And I'm going to find myself tangled up in confusion. So I'm going to start calling my objects based on their function. So I'm going to make a print writer called toClient, and the idea is this is going to be the thing that I use to send information in this direction. Alright, so how do we construct this? This is going to have to go inside a try-catch block because constructing a print writer can fail. Not just because, you know, the file method can fail, but the actual constructor itself, since we're constructing with an output stream. We can get a, oh, maybe it can't fail. Oh, but the socket will be able to fail, I think. So socket get output stream. Right, so that can throw an IO exception. So we're going to put this in a try-catch block. So toClient equals new print writer. And we're going to say socket.get output stream. So this is for writing to the socket. Alright, so what could go wrong here? Typical thing that could go wrong, I accept a connection, right? I get the socket that I'm coming from, and before I get down here to create a print writer, the client closes the connection. Right? As soon as the connection is accepted, the client closes, and now there's nothing sitting over here to send to. And when I try to construct a print writer to talk to this socket, I may throw an exception. So if that happens, we'll print out an error message and we'll just return. Otherwise, toClient should be something that I can write into. So now we can send a message to the client. So we'll say hello from the server. And that's all our program's going to do. Alright, so let's go ahead and run that, and let's try our telnet client again. Again, we're developing the server side, we're using telnet for the client side for now. So we'll go ahead and we'll say telnet localhost port 1234. And we got our connection received over here. We did not get our message to show up over here. Any speculation why that might have happened?
Can I see the code again?
What's the question?
Why didn't I get the message hello from the server when I connected to the host?
Did you actually send it yet?
Good question.
A flush with your print writer.
Yeah, so this is buffered. Because I'm using a print writer, print writers don't always print right away. They may buffer up, or in fact they will buffer up our output until later on when enough output has been sent to it. So let's try flushing our toClient. So this is a method inside print writer. Perhaps flush. So that flushes the stream. So let's let's compile that, let's run it, and let's do our telnet connection again, and guess what? We got our message from the server. And if I had done this from a different machine on my local network, right, this would still work. I would, instead of saying localhost, I would put in the address of this machine, 192.168.0.101, and this Java code would still communicate with that that client. So I was hoping to open up port forwarding in my firewall so that we could run telnet from the Linux server and connect to this from another machine. But I've got two firewalls I have to go through, and then some other stuff came up last night, and so I didn't get a chance to do that. So you have to take me on faith, or do this on your own, right? That this is actually going across the network, even though it's on the same machine. It could be coming from, you know, anywhere on the internet, as long as the firewalls allow access, which right now would be blocked. All right. Well, this is one piece of the puzzle, is having the server send information to the client. We can use a scanner for the other side, which is we want to read information from the client. So let's construct a scanner object so that we can ingest. So we'll make a scanner called from client, and then we'll construct that. And sockets come with a method called getInputStream. And scanners can be constructed with an argument that is an input stream. And so we can put these together. So from client equals new scanner sock.get input stream. And this is for reading from the socket. And if anything goes wrong, we'll say error opening scanner and print out the error message. Otherwise, we've got our scanner for reading in. All right, so pictures are really helpful with network stuff. So here's the server. Port 1, 2, 3, 4. Here's the client. And from the server's perspective, we have a PrintWriter called toClient, and we have a scanner called fromClient. All right, so we're going to make a really useful server. We're going to make the shout server, right? That whatever you say, it shouts it back at you. So, make a shout server. So we'll use has next line. We'll see if there's a new line coming in from the server, from the client. And if there is, then we're going to say toClient dot print line. How fancy? I won't get too fancy. I'll break this out into pieces. So line from client equals from client dot next line read one line from the client. Then I'm going to say print line from client dot to uppercase.
Is this going to be posted on campus?
Sorry?
Is this going to be posted on campus?
Yeah, I'll post this on the server.
Okay.
All right. So while there's another line available from the client, I will read that new line, save it in this variable called line from client, convert it to uppercase, use the print line method from to client to send that back to the client, and then I'll flush. And I'll do that in an infinite loop. And let me put this back up here. Alright, so make a shock server. Alright, this will almost compile. Oh, actually it did. I thought it would make me do a try catch. This is going to throw all kinds of exceptions if the connection suddenly goes away. But I guess it's okay with that. So let's run this. So we'll say Java main, and now we can do our telnet connection from here. It received a connection, and I can say this is a test, and it shouts back at me, this is a test. Right, so you know, I could throw some clickbait on here and retire, right? Maybe. So that's a full-blown, you know, client-server deal going on right here, right? I can send information, I can get information back, and I'm kind of, you know, cheating by I haven't written any client code. I'm just using telnet, but you know, that's demonstrating what the server is doing, which is get a line, send back a line. Now if I close my connection, and so telnet, remember we have this control right bracket, and then we can, you know, send commands to telnet like help and so on and so forth. So I can say quit, and when I do that, my Java program exits. Why? Because my Java program was sitting in this call to has next line, and has next line came back false because the connection to the socket closed. And so it exited from that loop, and that was the end of that. So I could throw some more debugs in here. Telling me the connection has closed. And I could print a debug in here. And just sort of echo the line that I'm receiving. And now if I run this telnet command again, I can say this is a test, and it tells me it received the message, this is a test, and it sent the uppercase version back to the client. And I can say goodbye, same thing. And then when I close out my telnet session, it tells me the connection is closed and says goodbye. Alright, let's add one more embellishment and then we'll take a break. Let's limit this to 3 messages. So we'll start off with a message count equals 0. And each time we get a line and we send it back, so the message count will tell us how many messages we received, and then we'll say if we've done 3 messages, That's the limit. So we'll say to client print line and we'll just rudely say goodbye. We'll flush that message. And then we'll close that socket. And then we'll return. Alright, so we're just adding a little more behavior here. Alright, so now if I do my telnet connection, I can say hello, this is fun, how are you? And then after it sends back that last echoed message, it'll say 3 messages is the max, goodbye, and it closes the connection, and my program terminates. Alright, is this making sense?
So what if you want to connect to a whole different machine instead of local?
Sorry, say it again. What if you want to what?
Connect to a different machine instead of the same machine using localhost.
Just put in its IP address. So right now,
And you see that.
so on my local network, this laptop that I'm pointing to right now has the address 192.168.0.101. So in here, I could use that address, right? And if I use a different address, it's not going to work. But if I use 101, that connects me to this laptop. But if I was on a different machine, I could put in that same address, and it would go through, my local network, go into the router, and connect to the laptop, and find the code that's listening to the server socket. And if I didn't have a firewall, I could go to a machine, on campus, for example, and run this telnet command, and it would route its way through the internet into my office here in the house and talk to my laptop. All right, let's take a 5-minute break. We'll come back. I want to talk a little bit about this whole business of routing and IP addresses and stuff like that, just because it's kind of good background, and a lot of people already understand this. A lot of people have kind of picked it up from setting up routers, or maybe setting up a network for your parents or whatever. But I want to just kind of run through that a little bit, and then take a little bit of a look at what's going on kind of at a deeper layer. This business of TCP/IP, and I'll show you a bit of the stuff from that. And then we'll talk about what makes this more complicated, because this is a pretty simple set of code here, and it's working pretty well for this, but we're going to layer some stuff on top of that. So let's come back and current inflation rate 9.62%. Well, that's sweet. Let's come back in 5 minutes and move our portfolios around during that time. And then we'll talk about some more stuff. Alright, so we'll take a bit of a break. All right, welcome back. Yeah, that's a bad inflation rate. Economics never made sense to me, though. I took an econ course, and they explained all this mathematics for why prices and inflation and all this kind of stuff do the things they do. And it's like, well, just change the knobs to this and everything will be great. And my teacher was like, no, it doesn't work that way. But with no explanation for why it doesn't work that way.
That's what happens when you have 30 competing economic theories.
Well, yeah, exactly. And theory is an interesting word to use.
Yeah, I think theory is a bit of a stretch.
Yeah, I mean,
uses of the word.
yeah, definitely closer to like ritualistic beliefs, maybe.
Hypotheses, even.
Yeah.
I think a lot of it might be wishful thinking.
Mm-hmm. Yeah, and it's a moving target, I'm pretty sure. I don't think the economy, works under one simple model. I think it changes over time. And unless your model is very sophisticated, it probably, does not take into account unplanned things like, war or disease or the singularity or whatever. So, yeah. I wouldn't mind taking an econ course again, though, because I'd actually pay attention this time. I don't really have anything prepared for this topic, but I was going through emails. I'm getting a lot of emails from students. I looked over the past 3 weeks. I've gotten 400 emails in my Clark address, and I've replied to 150 of those. So, and I don't reply to emails usually unless it's coming from a student. Most of the email is stuff from the college going out to like the all user list, and then lots of people saying like, don't send this to the all user list. And so 150 replies means, a lot of these are emails that are pertinent to me in terms of the classes I'm teaching. And so I'm seeing a lot of emails, and if I look on Discord, I'm seeing a lot of comment on Discord, and I'm seeing just kind of a general sense, and the word burnout keeps coming up. Lots of people are feeling burned out, and talking about burnout and talking about taking breaks and that kind of stuff. I don't know what my purpose here is in this unit, but I just kind of got the feeling that maybe we should talk a few minutes about this. Because this is definitely a part of among other things, being in the tech field. There's a lot of burnout in the industry, and I've gone through this myself. In the mid '80s, I went through a really bad job that drove me away from computer science for a number of years. And I've responded to some people when people have written me about this, and so some of this may sound, like I'm repeating myself. But I mean, I guess the main things I want to say are number one, burnout is a very real thing, and it comes from some obvious factors like having a lot to do, right? For example, just a purely hypothetical situation, taking physics and having to do a bunch of homework for that, and maybe taking a math course where you have to do, 50 problems a night to get your homework done, and maybe taking a programming course where you've got a new programming assignment every 2 weeks, and the next assignment is presented before the first one is even due. And all of this stuff entails a lot of work, right? But it's also aggravated by, having more limited time, for example, if you're working or if you're, eating or sleeping, and that cuts into your time. And I was talking to someone else about this, and she suggested that feeling trapped or feeling like this is sort of a critical do or die proposition makes all of this a lot more potent. If you're feeling like, if I don't pass this course, then all these dominoes will fall. And frankly, that's kind of, what happens for a lot of us, right? If you're getting financial aid and you don't pass a course, a lot of things happen as a result of that. A lot of extra steps have to take place to sort of set those dominoes back up. And so that creates, this big mental burden, and it makes, the question of, can I fix this syntax error super critical, right? It's not just a missing semicolon, it's my future, it's my financial aid, it's my transfer to a university, it's my being able to, stop doing a job that's physically breaking my body. It's all these things. And when a missing semicolon, carries that much weight, that's a great breeding ground for these feelings of burning out, and that's pretty terrible, right? It's a failing of the way all of this stuff is set up, in my opinion. But we don't have a better solution at this point. I wish we did. I wish people could study stuff they were interested in, and pursue it in a way that addressed whatever part of them resonates with the material and the subject, and not worry about all this other junk. But we're not there, right? I like to think we're moving there. I like to think that someday we'll have the Star Trek model where we're not so hung up on economics and profit and buying and selling. We can actually embrace ourselves and our human potential and each other. But we're not there yet. So I don't have a prescription for addressing this, but I think the first thing is being aware that this is real. And there's a lot of joking about it sometimes. When I was in a doctoral program in mathematics, everybody was always joking about how terrible their life was, and how they were wasting their 30s and all this kind of stuff. But it's real, and trying to pretend that it's not a thing doesn't really help. Wallowing in it doesn't help, but you got to acknowledge, that if you're feeling this, it's probably because you are doing a lot of different things and you're working on something very major, right? And so acknowledging that and maybe making plans to recharge, right? Now I've set up plans of study for many of you, and there's very little break. It's 3 courses every quarter, including summers. And as we were saying earlier, the summer quarter won't even finish when you start your fall semester at WSU. There's actually an overlap. And that's challenging. But if you can find ways to have breaks to some degree and take advantage of those, I think that's helpful. Yeah, senioritis is another version of this, although that's a little bit more fun because that usually involves, hanging out at the river or something. But same idea, right? It can make it really difficult to kind of push through the last part of something. Sometimes this is called smelling the barn, right? When you're on a horse and you get almost back to where you started, the horse starts to smell the barn and it gets very agitated, right? That happens with school and with large projects in general. And that can make it really hard to focus and concentrate, and maybe you're very excited about what's coming next. That can be just as hard as, just wanting a good night's sleep. And I guess I'm just going to say, being aware of it is critical. Respecting whatever it is that you're going through is critical. Don't beat yourself up for it, but pay attention to it. Your mind is brilliant, right? And it's insightful, and it knows you better than anything knows you. And so what you're feeling is usually not just random. There's usually a reason for it, and I think paying attention to that is an important part of this. And if you can take a day off sometime, that can be fantastic. Or take a day off from school this point and take a day off from work some other point. Not always an option, I understand. But anyway, I just wanted to acknowledge that, I understand that this goes on. I've been there myself. In my case, it drove me out of the entire field for a good number of years, which wasn't necessarily a bad thing for me. I switched from computer science to mathematics, and that was actually a really good experience. But it's probably preferable, if you're working this hard on something, to at least see it through, and then decide if you want to make some course corrections. And that's something to be open to also. I went through several years of a doctoral program in mathematics and eventually decided that that was not what I wanted to do. And that was hard because I had spent so much effort and time and energy pursuing this one goal, and it was always like, well, I'll just get to this and then I'll decide what to do. Okay, well, I'll just get to that and then I'll decide what to do. And at some point I just had to decide, okay, I will get to this point and then I will decide. And if I'm not having fun at that point, I'm done. And I worked that point for about a year, and just wasn't what I wanted to do. And people said, "Oh, you've already done a year on this. You just have to do another year, and you'll be done." But at some point, you can just say, I need to reevaluate, and that can take a lot of different forms. So anyway, I just wanted to mention that just because, like I said, I've been seeing a lot of it lately, and hearing it and feeling it in interactions with people, and if anybody wants to talk about this more, email or Zoom or whatever, we can certainly do that. I don't have particularly great advice or anything, but I do have some experience, so for what that's worth. Yeah, definitely.
Yeah, sort of like in my position, I mean senioritis. It's sort of that voice in my head that's saying like, hey, you don't actually need to finish your degree to do what you're doing next. Like, I had a change of plans in life, and so I don't really need to finish this, but it's sort of bad to think that way, because then, you don't try. What if you need it later? So I try to keep a positive attitude on that.
Right.
Yeah, fortunately or unfortunately, I've experienced senioritis in high school before, so at least I know what it feels like.
Right. Yeah, and path changes are interesting. So I don't know how many of you have read Joseph Campbell, but there's a quote from him that I won't do justice to, but that I've shared with a number of students. He talks about so he writes about the hero's journey, right, and about following your path. And one of his quotes is something to the effect of you don't know what your path is until you walk it. And if you see a path laid out clearly in front of you, with each step marked very plainly, it's probably not your path. It could be, but the fact that you're seeing it means it's a path that somebody else has walked. And it could end up being that that's your path, but you don't really know until you're walking your path. And each step you take defines the next piece of that. And so I grew up in a household with a dad who was an engineer, and two parents who were amazing to me, and made it very clear that I was going to college and so on. And I never really thought a whole lot about what I was doing. It was all kind of like automatic. It's like, of course I'm going to finish high school, and one Saturday I was walking to school to take the SATs. I didn't think about it. I didn't wonder what this meant or anything. It was just the thing I was supposed to do that day. And I lived that way for a long time, through college, through first jobs, and so on and so forth. And that's fine. That can be useful. That can take you to some very good places. But sometimes you find something very different, where your next step is falling, and it's important to notice those things, and at least be open to them. And if you decide I really want to be doing this one thing, go for that. If you've got passion for something, definitely that's a good place to be. But yeah, life is unpredictable. I've told some of you this before, but one of my best friends, when I was in the math program, he was studying a field of math called L2 cohomology. It was a very specialized area of mathematics, and a lot of the research at the time was coming out of Japan. And so we all had a language requirement for our PhD program. His language requirement was going to be Japanese. So he learned Japanese and he passed his test. And he eventually wrote his dissertation, got his PhD. And, there were like 5 jobs available in the world that year for L2 cohomology PhDs. And so he, got a job at a small college somewhere. And anyway, long story short, eventually he was contacted by a travel agency. And they were looking for somebody who was fluent in Japanese who could work with them to arrange tours for people from Japan who wanted to visit Hawaii. And he had, all of these credentials from getting his PhD. He was, articulate and creative problem solving and all that kind of stuff. That's what he does for a living now. He works for a travel agent. He lives in Hawaii, has a fantastic life, right? And when he started his PhD program, when he chose L2 cohomology as a field, I'm sure he had no idea that he would end up living in Hawaii, helping people from Japan take vacations. But that was where his path led him, and I enjoyed knowing that because my path is unknown. I'm teaching right now. I don't know what I'll be doing, a few years from now. But being open to what comes and being able to take advantage of opportunities when they present themselves, I think those are far more powerful than, having a plan written in stone that you fight the forces of the universe to stick to. Alright, from there we're going to segue over to routers and IP addresses, which is the next logical topic after life.
I feel like routing tables, IP addresses and stuff helps make them feel better. So.
Yeah, totally. And that's about packets finding their path through the network, so it's all related.
Have you been writing the those timestamp labels?
Yeah.
Okay.
Yeah, so those should be popping up in the video. So, we have this thing called the internet, and it's, a bunch of machines with connections between some of them. I don't know how the internet works. I suspect somewhere somebody might. Vint Cerf probably does, but it's there and it works, right? And someday maybe it'll be like Stonehenge. People will find these routers and these connection points and speculate, what this was for. But it works, and we're going to look at a really, really simplified view of this, which is we can just sort of imagine, a set of machines, And on each of these machines, you know, there's these sockets. I haven't seen on the screen share. Okay, they should be popping up. Here's a test tag. So.
Okay, never mind. I'm just blind.
Okay, no. So when I have, like, you know, stuff like this up, they're pretty hard to see. So they're easy to miss. So we have these machines, and they have, you know, things like server sockets sitting on them, which have port numbers. So the first thing is, how do we find these machines, right? So there's some sort of IP address, and this is this, you know, formerly 4-part 32-bit number that uniquely identifies each machine on the network, right? And so, you know, 32 bits, 4 billion possible addresses seems like plenty if you go back to the 60s or 70s. But well exceeded a number of years ago. So these numbers uniquely identify a particular machine. And if we forget about routers for a minute, if we just think of these as bare machines, right? Basically, when I want to send a message to a machine with a certain address, well, I have on this machine information about how I can get to a particular address. And so these addresses are you know, functions of what these first parts of the address are. And so when I started doing this, which was, you know, mid 80s, there were two sets of addresses. There was 10 point something, point something, point something. This was called ARPANET. This was the Advanced Research Projects Agency, which later became DARPA. And then there was 26 dot something dot something dot something. This was MILNET. So this was the version of the network that was being used for research and for schools, and this was the version being used by the military. And that was it. Two sets of addresses, 10 dot something, 26 dot something. And so, you know, it's a pretty simplified routing question then. If I want to talk to 26002, I have to know which machine is connected to that, or which machine knows how to get to that. And so we had routing tables on these machines that would help us take a packet and send it to the correct destination through some series of links. And so now, you know, we've got all kinds of things with this first piece of the network address, and there's no formal ARPANET or MILNET anymore. But it's the same general idea. And so through some sort of magic of routing, and you can pull up the documents to see how this works, right? We can ask to connect to a machine with an IP address and make contact with that machine. And then we usually have this port number if we're trying to talk to a server, so there's an extra 16 bits, and that specifies some particular socket on that machine. And there's a process running somewhere, hopefully, that is listening for connections on that. That process is a server, or the older term is daemon. And so SSHD is the server or the daemon for the SSH client. Telnet-D is the server or the daemon for the telnet client, and so on. All right, so you can go back to 1981. And so this is something called an RFC. An RFC is a request for comments. And RFC 793, September 81, this was a request for comments on something called the Transmission Control Protocol. So this is TCP. And we hear about, you know, TCP/IP from time to time. So if I do a netstat, I get a bunch of information about connections on my system, and a bunch of these, that's a lot. a lot of these, the protocol is listed as TCP. And all the stuff we're doing in Java right now, server sockets, when we're using telnet, we're using this protocol called TCP/IP. Good question. So, IP addresses are already, so IPv4, the 4-part address, usually we write them in decimal, and each of these fields is from 0 to 255. We could write them in hexadecimal. That doesn't actually get us more combinations, because then they would be 2-digit hex values for each field. But usually these are done in decimal when we see an IP address being mentioned. 192, 168, those are decimal numbers. But if we convert them to hex, there's sometimes useful information in there. So what's 192? That's 128 plus 64. So our local networks usually have a first piece address of C0. And 168, I don't know why they pick on 168, but that seems to be. But we've already exceeded the 4 billion, and so IPv6 uses a 6-part address. And if I run ifconfig, there's a 6-part address for my Wi-Fi. And I have not played around a lot with IPv6. IPv4, these plain old, 32-bit addresses, that I've played with from the ground up. I've done, low-level packet disassembly and assembly, inside cable modems and such. But I haven't messed around with IPv6. In fact, I have to run to Stack Overflow every time that I'm forced to interact with it. But it's punchline, it's got a bigger address space. So a lot more addresses. Primarily because, we've got the Internet of Things, right? And so it's not just, 4 billion people using a machine. It's like every cell phone, every smart toaster, every fitness tracker, right, that can be Wi-Fi accessed has some sort of address, right? They don't all have, addresses that can be hit directly from, somewhere else on the network, but they have, some presence in an address space, and so 4 billion is not even close to enough. Smart toasters are good. Anybody ever see a dot matrix toaster? It's like a dot matrix printer, but it has a matrix of heating elements, and so you can put your toast in and program it to light up certain elements to burn particular patterns or words or characters into your toast. It's a brilliant idea. All right, so this was the request for comments. This was basically a proposed protocol for doing this communication from machine to machine across a network. This was developed by DARPA. That's the Defense Advanced Research Projects Agency, I think. DoD, Department of Defense. Prepared for DARPA. And this is a glorious document. If you want to really understand TCP/IP, right? These are the source, right? This was where all of this came from. This was the paper that was looked at and discussed and debated, and then used to build the first hardware and the first software systems that used these protocols to do networking. So this is 85 pages of typewritten text. And you can read, all about it, the motivation, the idea of, networking as a thing, and so on. And there's great ASCII art in here, right? So here's a simple 4-layer view of the network. So we usually think about a 7-layer stack of protocols for TCP/IP, for networking. But here's the basic idea. Higher level, these are things like telnet, or today SSH, or your mail client and your mail server and so on. These are the programs that rely on networking. And the idea is that these programs interact with this layer called TCP. And TCP is built on top of another layer called IP, Internet Protocol. And IP is built on top of another layer, which is the communication network. And this is usually presented as a 7-layer stack. So applications, transport, network, and physical. So there's from 1981's RFC, application layer, transport layer, that's TCP, internet layer, that's the internet protocol, and network layer, that's the communication stuff. So this down here, these two bottom layers, this is the physical stuff. This is the cable that plugs into the little thing sticking out of the wall, right? This is the transmitter that sends the 2.4 gigahertz signal, or that receives a signal and translates that modulation into ones and zeros, or the phone line that carries the tones that are used to do SLIP, right? Serial line internet protocol, and so on. So these bottom layers here, this is the physical stuff. This is the low level, the engineering stuff, right? The things that you would cobble together out of physical stuff. This is the layer that represents, sending information from one of these things to another. So if you have a remote control and you hit a button on it, what does it do? Well, it generates a waveform at a certain frequency, and it modulates that waveform. And maybe it modulates the frequency, or maybe the pulse width, or something like that. And so the physical layer would be, the infrared transmitter and the receiver, but there might be a network layer on top of that which says, hey, when I want to send a 1, I'm going to send out a 25 kilohertz signal for 2 milliseconds, and I'm going to leave it high for 25% of the time and low for 75, so it'll have a 25% duty cycle. And when I want to send a 1, it'll be the same thing, but it'll be a 75% duty cycle. And so that's this network layer. The transport layer is, how do I get stuff from one machine to another? So all of this business of addressing and so on and so forth. That's what TCP is all about. And then these higher level layers, this is a breakdown of the stuff that you code that actually depends on internet connectivity. And it can be broken into these sub layers, but it's basically higher level applications. Let's see, a military data link system. So it depends. Pretty much any system that's going to use this kind of networking as we generally use that term will probably have all of these layers to it. And part of it would be a transport layer, definitely. But yeah, it's the realm in which these things are being used is probably independent of this. But that being said, there might be reasons why you might do something different than this layer, and military could be one of those. So let's find some better ASCII art in here. So this is all important stuff, right? So how does basic transfer work? What about reliability? So this was done originally in an era when reliable communication was not guaranteed. If you sent something across a cable, you could not guarantee it would be received correctly on the other end. And so where are we going to do the checking to make sure that things were transmitted correctly? How are we going to correct the situation if things are not transmitted correctly? That's all part of these specifications. Let's So examples of application layers, voice, pretty far looking, right? TCP, Internet Protocol, and then local network. So let me show you what this actually looks like. Here's a TCP packet, right? You got to appreciate the ASCII art here, right? 32 bits. They're numbering the bits from the left. That's okay. So when you want to send a TCP message from one machine to another, here's what you send. 1, 2, 3, 4, 5, 6, 7 times 2, 14 bytes plus, however much data. So 16 bits specifies the source port. So when we make a connection, right, that's the source port. I'm making a connection from this port to port 1, 2, 3, 4 on this machine. So you make a packet which says, there's my source port number, there's my destination port. A sequence number, so you can assign a number to your message, because your message, if you're sending, a million bytes of information, you don't send that in one big TCP packet. You break it into pieces. And so you can put a sequence number in there. Various flags, checksums to ensure that the data you see and the bits you see in this header are meaningful. So, add up all the bytes, reduce it modulo 256, and then complement all the bits. And maybe that's your formula for doing an 8-bit checksum. But this is a 16-bit checksum. So it's a way to know if any of the bits in any of this got flipped. And then there's some padding at the end, and then here's the actual data that you send. And so every time that you send something across the internet, there's a TCP header assembled containing data that, among other things, includes the information you're trying to actually send. But that data packet is, to a large degree, made up of RFC 791. So this is the Internet Protocol. This is the IP part of TCP/IP. And if we just go down to the ASCII art for this, there's what an IP packet looks like. And part of the IP packet is this 32-bit source address. What address are you sending from, and destination? What address are you sending to? You need both of these. The destination address is how it gets to you. The source address is how you can respond. Total length of the message, time to live, so these messages can expire, more checksums, and so on and so forth. And so you have data you want to send, you put that into a packet that is a TCP packet, which encloses an IP packet to actually route from one machine to another. And you have software running that when it gets a message from the physical piece of the network, right, from the cable, from the Cat5 line, from the Wi-Fi receiver, whatever, when it gets that collection of bits, it interprets it, right? It breaks it down into, here's what these bits mean. It's coming from this port, it's coming from the destination. Here's some data. What's the data? Well, it's the version of IP and so on and so forth, and it interprets all that, right? So PA5, we're doing networked communication built on top of all of this stuff, but you're also creating your own interface, your own language for communicating between the two ends of your game. And so this 3-message protocol I suggested: first message, you swap names; second message, you send mouse click coordinates; third message, you can say quit. And so all of this is being applied underneath to ultimately deliver, in that case, a single line of text. And then you're writing Java code that will interpret that and say, oh, I got message C1015. That means the other player clicked their mouse at position 1015. Okay, I'm going to go ahead and run my code that responds if the other player clicks at 1015 to, turn on a line, complete a square, change whose turn it is, print an error message, whatever's going to happen, right? And so there's always this layering going on. And one of the aspects of this layering, one of the things that's made this work so well, is generally each layer talks to the layer above and below it. But I would never write a piece of Java code that was responsible for driving the 2.4 gigahertz transmitter in my Wi-Fi card, right? That's not the job of my application program. My application program says, open the socket, send this message, receive this message. The physical layer, there's something there, there's code, sitting inside a PIC processor, maybe inside my Wi-Fi card, which is saying, oh, okay, we have to turn the transmitter on, we have to send this modulation, we have to do this encryption because this is a secure connection, and so on and so forth. But these layers aren't interacting with these layers. These layers are interacting with each other and maybe with the transport layer. The transport layer, TCP, talks to IP and it also talks to the application. TCP does not interact with the physical layer. IP might, right? Or it might talk to a data link layer, and the data link layer talks to that low-level physical stuff. So there's always this hierarchy, and we can, extend this hierarchy in our own minds or in our code as we write, programs that use networking. And so I would say there's, a netdot layer on top of this, which is responsible for sharing information about the state of the game with each other. So these are fun documents to look at. If you Google RFC 791 or RFC 793, you can pull down these files. And like I say, if you really, really want to understand what's going on, this is the source, right? And I've occasionally had to go through here when I've done some work I was doing with a networked multiprocessing system. And I was getting really weird, quirky stuff, and the answer to my issues were actually in this TCP document, and it talked about setting timeouts on certain conditions, and I needed to change the default handling to something different. So these are good documents to know about and to occasionally refer back to if you like. So where do routers come in? I tagged this routers, but this was really about more stuff. But where do routers come in? So here's my machine. Here's laptop 1. Here's laptop 2. And I call this machine 192.168.0.101. And I call this machine 192.168.0.37. And I chose these addresses so they'd be easy to remember. And I could have these addresses assigned more or less at random when my machine boots. But I just decided, this machine's going to be 37, this machine's going to be 101. And I've got those written down somewhere, right? And I've actually got, tags on the physical cables that have these numbers printed on them. And so if this machine wants to talk to 37, it goes over here. This can talk to 101 and so on. And I've got, phone 1, phone 2, phone 3. I've got a printer. I've got, 3D printer. And all this other stuff sitting on my local network. And they each have, their own IP address. That's this thing. And whatever code I want running on them is running on. My 3D printer is running something which listens for connections on a certain port, and when it receives those connections, it will ingest a 3D print file, a list of commands for the servos on the printer, and then send it to the printer and print an object in the garage. And so I don't have to physically get up and walk to the other room, which would be way too much exercise. So all these machines are sitting out here, right? But none of these machines are accessible from the outside world. These are all kind of connected to each other through something called a router. And my router has some address that's fictitious. I'm sorry, whoever's address that actually is. But, you know, some sort of address. And there are other systems out there, probably with routers, with addresses, and these can talk to each other. So if up here is, you know, google.com, and I want to access their web page, well, from this laptop I can go through my router and say, hey, talk to port 8080 at google.com, and there's address resolution protocols at place that will take something like google.com and turn it into an IP address so that we can put those numbers into that piece of the IP packet, right? And then we can take our message, put it into a TCP IP header, send it out to the net, and it will work its way from machine to machine and eventually find this machine, talk to port 8080, there's code listening on that socket, and it will go ahead, create a new socket, start a two-way communication. And since I'm originating my message from here, right, that message has information about how to get back here. And so two-way communication is possible. But if someone at google.com wanted to access my laptop, they can't do it. They can access my router because they know the IP address, but they can't get past the router, right? If they try to open a socket at this IP address, right, well, the router is looking at it and is saying, I don't know what you're talking about. So that's the sense in which this is a firewall, right? It blocks incoming traffic from getting any further than this, unless you open it up. And so if I want someone from Google to be able to play NetDots on my machine, what I can do is I can go into my router and I can say, hey, if you get a request to connect to port 1234, send it to laptop 1. Well, now I've opened up a hole in my router. And if someone from, yeah.
So is this how, for PA5, is this how someone's going to be able to connect to the server host?
Yeah, so if you wanted to try your PA5 on two different machines on totally different routers, so for example, one of them is at your home and another one is at a friend's home, right? You would need to do some kind of what's called port forwarding for somebody to be able to get through the router.
I have heard about port forwarding because we had a guy we got on our internet earlier, probably like a few months ago. And he's mentioned about port forwarding can be dangerous because that means that anybody that has access to your router can go to that port and do something bad to it.
Yeah, so I don't recommend doing this unless you're pretty confident about what you're doing. This is basically the same thing as if I took this laptop and plugged it into a network connection that was accessible from the world. And if you do this with a Windows machine, they call them honeypots, right? They do this for security. Sometimes they'll just take a machine and put it on an open network connection, and it's a non-stop stream of infiltration attacks coming in. And you know, a well set up system will deflect most of those, but just the overhead of managing all of the incoming attempts to find open ports, to guess passwords and so on and so forth is enough to make your machine essentially unusable. So generally, you know, we have a good router that manages all of that stuff and blocks most of the incoming traffic. And all of these machines sit on a local network where hopefully, you know, my phone is not trying to break into my laptop and so on. But once you go out on the actual net, it's a mess. It's just nonstop attack attempts coming in. And so if there was a vulnerability in, you know, the operating system you were running and you hadn't patched it and somebody wanted to exploit it, right, they can do it whether you're plugged in directly to the net or you have, you know, some kind of port forwarding turned on. Now theoretically, you know, if this is just going to, my shout server code that I had, someone's not going to hack me because of that, right? Unless there's a buffer overrun bug in the string class of Java that has never been reported and somebody can use to start, accessing memory outside the Java virtual machine. And then, who knows? That's the nature of these exploits. That's the danger of day zero weaknesses, because until vulnerabilities are patched, right? Well, that's what a vulnerability is. It can be taken advantage of. So usually we don't forward any ports from outside to our machines. If you try to ping this machine, you won't get a response, right? Because the router is simply not passing that information through. Now, if you're running a Minecraft server and you want friends to be able to come in and access that, right? You take the port associated with the Minecraft and you say, okay, forward that to, this server 1 at this address, and any network requests to this address to that port will get forwarded to that port on this machine. So it's a way to say, hey, if you're coming in from outside, this is all you know about. But for that port, I'll give you access to this machine. And it lets you run a server that other people can connect to. Now that has to be done because that's what the network is, right? So someone has to be able to do that safely. Yeah, go ahead.
I was gonna say, is there a way you can actually, like, if you get a network request to connect to someone connect to your system, is there a way you can, like, allow or disallow that, kind of like to make sure that whoever's connected to your system is someone you at least know?
So I'm pretty sure most routers let you specify details of the address it's coming from. So you could say you have to come from this particular address, or maybe you can wildcard this set of address ranges is allowed to forward, and anybody else will be blocked. You can probably whitelist particular addresses that way, or block certain addresses, so that there are levels of control in here. And that's why I say this is stuff that, if you're confident about what you're doing, you can do it safely. But you've got to understand your router, you've got to understand the implications, you've got to make sure that the machine that you're exposing any port on is extremely secure, and doesn't have, any of the countless numbers of vulnerabilities that have been discovered over the past few years in particular. And places obviously do this, right? Anybody who has a web server, right, has, some sort of setup, probably port forwarding, to let the outside world get to particular ports on certain machines. Any Minecraft server you run, any time server, if you try to synchronize your clock to NIST, right, to automatically get the accurate time on your system, right, you're making a connection to a server somewhere, and eventually, you're connecting to a particular port on a particular machine whose job it is to, send you the current time. But it gets hairy, and trying to lock down a machine is a whole job in itself. To make it really hairy, there's a DMZ. Some routers, I think, don't even have this anymore, but a demilitarized zone. You can actually open up a whole address space and undo the protections that are kind of inherent in the router, and just say, okay, so these things are open up to the world, and that's something you would do if you wanted to see what was going on in the wild world. And see how many attacks are coming and what regions they're coming from, and so on and so forth. You can open things up like that. So my home system, I had a router that came built into the cable modem because I've got cable service, and that worked great until one day I was having trouble connecting to something, and I looked, and something had reset my router password. Right, the router had factory reset, which means it went back to the default password, which was like, Motorola or something like that. And that's a horrible vulnerability because, from anywhere you can connect to a router, and if you know the administrator password, you can go in and do whatever you want. So you definitely want your router set up, with good password security and so on and so forth. And for me, I actually have two routers. I have the cable router that came from the cable company that apparently can be factory reset by someone else, and so I just use that as a conduit from the cable into my internal router, and then this one I control. So why is it so hard to find a router with hairpin NAT functionality? I don't know. I mean, you can make your own router. There's tons of information out there on just making a dedicated Linux system that just works as a router, maybe using a Raspberry Pi or something. If you want to really get a lot of control over it, you can definitely do that. That's the opposite of what I have time to spend on, but it can be a lot of fun. My brother is really big on networking stuff, and he can talk circles around me on all of this. Yeah, cool. So yeah, DNS is interesting, right? This domain name server business. When I want to telnet to Google, I don't say telnet to this, or I want to get a web page from Google. I don't use an IP address. I say google.com. Well, that has to get changed into a number somewhere. So there's this very old scheme for domain name service for translating names like google.com or clark.edu into IP addresses. That's what most people feel is the ultimate breakdown of the internet will be a DNS exploit, because if you can control what machine someone's trying to access, right, all bets are off. So DNS spoofing is a big keep people awake at night kind of thing. But yeah, you can do your own DNS serving. And if you've ever used a Raspberry Pi, right, you can put it on the network and you can access it by name, and it's usually whatever the host name is. You can say hostname.local, and there's a local DNS server that runs under Linux and Raspbian, and under Windows, if you install certain printers, you get a DNS server, and then you can start doing this. So a lot of people install this print driver under Windows just to get the DNS capability. So this is at least a whole third or fourth year course at a university on networking and all of these details of it. We don't need to worry about these for the most part, and we definitely don't need to worry about these for PA5. We're just going to say, open port 1234, make some sockets, and share information. And this can be a pain and very annoying. When I do 223 at in person, it's a bit of a nightmare. So I used to bring in a router that I would just hook up in the back room, and I would have that available for students to just connect to do this kind of stuff, and they made me take that down. They thought it was like bringing down the whole building's internet, and bandwidth is a challenge, and Wi-Fi is a challenge. And so on and so forth, and trying to do some of the stuff at Clark, like if you log on to Clark's intranet and you have a laptop and you want to let somebody else telnet into, or make a connection into your machine, you can't do that, right? We can't just turn on port forwarding inside Clark's routers. We don't control those, and so this stuff is hard to do on a larger network. If you're at a big business, you probably can't just have incoming traffic forwarded to one machine. But on a home network, this works great, and routers are pretty affordable. Probably anybody who has internet access already has a router, right? Because they're pretty much built into modems now. So whether you're doing DSL or cable, you've got a router. And getting just a standalone router is, you can pick them up for $25. But there's really good ones and there's really inexpensive ones, and there's a whole spectrum. And a lot of these routers, they run Linux inside. There was a model of Linksys router a number of years ago that was really popular for Linux fans because it had an accessible Linux system inside, and so you could just use it as a Linux machine instead of a router. Let's see. Why does Zoom keep randomly capitalizing words in my sentence? Oh, who knows what Zoom does. There are so many things keeping an eye on what one types in a computer. And Outlook, I have to use Outlook for Clark, and Outlook is so like in my face, right? I'll get an email from Izad, and I'll get a pop-up window saying like, you have an email from 3 weeks ago with Izad you haven't replied to. Would you like to reply to that now? Or it'll go through my old emails and say, here's some suggested topics you and Izad could chat about, based on keywords from our last email. I mean, it's really kind of, and so there might be something like that's changing the text of what you're typing, possibly. All right, so that's a little bit about kind of what's going on behind the scenes with all of this stuff. And like I say, we don't really need to worry about this a whole lot for PA5, but it's I don't know what other course this comes up in unless you're taking a networking course, or you're taking a course where you're expected to know this. Yeah, go ahead.
I know that in WSU they have a lot of opera courses that go into things like internet security and cryptography.
Mm-hmm. Yeah.
So I'm not going to bring this stuff up again and maybe even go way more detail.
Definitely, yeah. So they have networking courses. They have a pretty cool crypto course. If you like math, it's a lot of fun. The stuff that we do really briefly in 215 with RSA, it's like a whole course around all that stuff and a whole lot deeper. And if that stuff is intriguing, that's a fun course. Some system programming courses, you'll get into some of this, but a lot of times people just kind of assume that, you're computer science, you know how this stuff works. And so I just wanted to do kind of a superficial, high-level pass over that. Wednesday, I wanted to dig deeper into Java. I want to go back to this code and talk about why this doesn't always work. And basically, we're moving in lockstep. We're receiving a message, we're sending a message. We're receiving a message, we're sending a message. If we can't guarantee that taking turns behavior, this gets more complex. And so this will get us back into threading, and dealing with that. So we'll talk about that on Wednesday, and then if there's no questions yet on PA5, I'm just going to try to do one more run through of PA5 from top to bottom and sort of do some more specific ideas for pseudocode for how to structure things in there. And then Monday, a week from today, I believe, is a holiday, so we'll miss that class. Wednesday, we'll continue with PA5 and networking, and then we're down to the last week. That'll be week 10 after that. And so we'll talk about a few more classes. Yeah, go ahead.
I was going to say, Monday is a holiday. It's also when our SLP is due.
Right.
Is that okay?
Yeah, that's Memorial Day.
I was going to ask you, like, how we can put this into PA5. Like, what... I mean, I'm not even talking about that maybe Wednesday, but I'm trying to think of how you can put this into PA5, or how it can be set up initially.
So there's that 3-stage protocol I suggested, right? So in the very beginning, when the server hits the start button or the client hits the connect button, you make a connection, right? On the server side, that means, make a server socket and say accept. On the client side, we have to do what telnet's doing. We'll go through that on Wednesday, but that's basically creating a socket for the given address and port number. And then, make a PrintWriter and a Scanner pair so that you can write to the other side and receive from the other side. And each side sends their player's name. So that's the first exchange that takes place. And then basically every time you click the mouse, send a message to the other side with a message saying, hey, the mouse just got clicked. So that was that second message type I suggested, the letter C followed by the X and Y coordinates separated by spaces. And we're going to have a separate thread running which listens for incoming information from the socket. And when it receives a message, if it's a C followed by 2 integers, it parses those 2 integers and then basically does whatever your mouse click code does. So it says, okay, the mouse just got clicked at, this XY location, and your PA4 code does whatever it does. And that's pretty much the whole gameplay. And then the last part is if you hit the quit button, send a Q through that message, and on the receiver side, if you see a Q instead of a C message, just go ahead and say the other player quit and shut everything down. So that's part of what we'll write out in some more pseudocode on Wednesday, and we'll also do the other piece of this, which is creating the socket itself. So doing the client side, and we'll end up with 2 pieces of Java code that can talk to each other, and that will give you examples of all the possible code you might need. Alright, so we are 2 minutes past time, so I'll leave it there. I'll see you in office tomorrow, or I'll see you Wednesday in class. Alright, thank you everyone.